All right, you guys, this one's on density and displacement. So the big picture here is, what if we just have a funky 3D shape, right? Like I pick up a random rock off the ground and I'm like, what's the volume of this weird thing? It's not like a triangular prism. It's not some neat shape. Well, the plan is we can submerge it in some kind of fluid and check how much fluid is pushed out of the way. So for example here, in this picture, we have, and I'm just going to take a color here and shade it over. Once we submerge this rock into the water, we get, it used to be here at the 150 line, and now we have it's at some other line here. So this volume, this cylindrical volume of water that got displaced, that's the volume of the rock. So by using water, and again, there's like, as long as it's non-permeable, so like this wouldn't work with a sponge, something that soaks up water. That's not pushing water out of the way. It's some is going in, some's getting pushed out of the way. And of course, it has to be like rigid or something. If it's something soft or squishy like a balloon, the pressure of the water will actually squeeze the balloon to be smaller. But if it's a solid object that's not like bendable, I'm going to squeeze it smaller, and no water's going in or out of it, so it's keeping its shape, and and not floating, right? Because if it's floating, only some of it is underwater and some of it is above. But if you submerge some weird 3D object under the water, you can see how much water is displaced, and by finding the volume of this, that's equal to the volume of the rock. That's the whole idea of displacement. And then we can measure other things with it. But that's the big idea of this whole lesson. Okay, now two definitions really quick. One we've already kind of gone over, but the other is density. Some of this lesson, it ties to real world. It's the idea of how much mass there is per unit volume. Or in other words, how many protons, neutrons, and electrons are shoved into a little area, right? A lighter thing like helium, which is just this big airy molecule with what's helium, like one neutron, maybe one proton, I can't even remember, and then just a little teeny electron floating around. So if you have a bunch of those in a container, it weighs almost nothing. I mean, 0.000020000, it weighs almost nothing. Whereas air is about 5 times or 6 times as dense as that. Means there's 6 times as many protons, neutrons, and electrons in the space because you have these molecules that have denser nuclei. So there's more protons and neutrons jammed together. And then there's like 2 electrons on this shell and more in the next shell and so on and so forth. Water, much denser. So again, when we're talking about 1 cubic centimeter, we're talking about, think of like a marble that you hold in your hand and then cut it in half. That's about 1 cubic centimeters worth of space. And so each of these has a different weight. 1 gram, I don't know, that's ballpark around a penny. Maybe a penny's 2 grams, or I don't remember the exact, but about a penny for how much that weighs. And then blood is almost twice as dense as water. It means if you took a cup of water and a cup of blood, the cup of blood would be almost twice as heavy, the same volume, but more matter in it. And then think about steel, almost 8 times as dense as water. Lead, 11 times as dense as water. Gold, if you've ever held a nugget of gold, which would be worth a lot of money, but if you ever held it, it is heavy. Or if you ever go to the dentist and they put on a lead vest to protect you from the x-rays, that thing weighs a ton, and it's this thin little vest. And then over here I just put in a white dwarf star. So a white dwarf star is when certain size stars collapse and basically get as close together as quantum mechanics will allow them without electrons and neutrons being in places that are kind of impossible for them to be on based on our modern understanding of physics. So if you squished everything together as close as it could be and it's crazy hot and squeezed together, you would have every half of a marble would weigh about as much as 4 Ford F-150 trucks. Or 5, I can't read my own writing. Think about that. 5 giant American trucks in the size of a half of a marble. Just think about a trash compactor or something squeezing 5 trucks down and squeezing it down. All that same weight, that same mass into a half of a marble. That's crazy. So that's the idea of density. One block that's the same size of 5 different materials will have 5 different weights, because there are literally more pieces of atoms, more protons and neutrons and electrons in that box than there are in the other thing, because some molecules only have like 1 proton or neutron in the middle, which is the heavy part. I mean, the electrons don't really weigh much at all compared to the middle. So really we're just talking about what the middle weighs. And some middles have all sorts of stuff. I mean, gold, if you look at the periodic table, has some crazy high, I don't know, let's make up a number and say 80 or something. And then you just go down, and PB for lead is, I don't know, let's say 60. We could look these numbers up and down until helium is one of the lightest, hydrogen being just the one lighter. Okay, that's what density is. Displacement we already talked about, but again, the idea is when you submerge, like how much volume does this weird piece of brick have? You put it in the water, and then you just check, oh, we went up 2 units, like, right, whatever the units are, but the volume of this space of water that got displaced, whatever the units are, 2 centimeters cubed, 2 milliliters, 2 whatevers, then the volume of that rock is 2 of whatever the units are. Okay, now let's do some problems. All right, so when you put a rock into a container of water, it raises the water level 3 centimeters. Now, you might jump and say, well, that's the displacement. Sort of. The key is, was it like a big pool that got raised 3 centimeters? Because we're looking for volume. So a big pool raised 3 centimeters is maybe a lot of volume. Whereas if it's a teeny tiny little graduated cylinder in your science class, and you drop something in and it goes up 3 centimeters, that's very different. We're talking about volume here, not just the height of water displaced, because the bigger the base times the height, the bigger the volume. Okay, so I'm going to delete that. Let's keep reading. If the container is a rectangular prism whose base is 15 by 15, okay, so we've got a 15 by 15 base. It goes up to some height that we don't care about. But what does matter is, okay, here's the original, here was the original volume of water in the container that keeps going up. When we raise this, oh, these colors look not so bueno together, but when we raise this 3 centimeters, what we're getting is a 3D solid with that same 15 by 15 base and a 3 height. So if we just erase the rest, right, who cares about what liquid was under it? What we care about is we raise this 3 centimeters, and it's a 15 centimeter by 15 centimeter base. So the volume that got pushed up to that new area is 15 by 15 to find the base, and then times the height of 3, so that's 225. Times 3, or what, 675. So the volume is 675 cubic centimeters. Right? Again, it didn't matter what the original height was, as long as the rock, right, goes in there and sinks below the surface of this water, so it's not sticking out into the air. What matters is we now have 3 centimeters more of height. And so you could think about it like we do the entire volume, so times x plus 3, that's the v like total, and then we subtract the v like, I don't know, a for additional, and that would be the 15 times 15, oh, I didn't mean subtract the original, I meant subtract the original. So we take the new total and minus the original, and sure enough, this is 225x plus 225 times 3, and then we just take away the original 225x, shoop, and there's the additional new volume. So you could think about it like that, but the big idea is new height times the area of the base, which is right here, 15 by 15. It's the same as the base of the figure because it's a prism. Boom. All right, let's look at the next one. You drop a solid glass ball into, I'm going to zoom in a little bit here. You drop a solid glass ball into a cylinder with radius of 6, okay? So we've got, let's go to some better colors here. We've got a cylinder with radius 6. All right, we drop a ball into it, raising the water level 1 centimeter. So maybe here was the original water level. Again, we don't care where that was. But then it goes up 1 centimeter. And this was in centimeters down here. And so the new volume, here's the new level, is, oh, I'm going to pause the video right there. Okay, I'm back. So the new volume then is base times height, because this is a prism. So we have pi r squared times height. This is a radius of 6. So we have pi 6 squared times the height of 1. Again, we're only looking at the displaced volume. We don't care about what the original volume was. Notice they didn't even give you the original height because it doesn't matter. And so 1 times 6 squared, that's 36 pi centimeters cubed, is the amount of water that was displaced when you put the glass ball in. So that's the volume of the glass ball. All right, so a fish tank, 10 inches by 14 inches by 12 inches, is the home of a large goldfish named Columbia. She is taken out when her owner cleans the tank, and the water level in the tank drops 1/3 of an inch. So a fish tank, it doesn't tell us which is the height. So this isn't actually an easy question to answer because there's 3 possible answers here. So it drops 1/3 of an inch. What matters is which of these is the length and width and height. In general, we usually do like the base here. Doesn't matter length and width. And then by the height. Now, in general, like there isn't a single convention for this. Usually when you look at things online and you look at the specs, the 3rd dimension is the one you don't care about as much. So like if you're looking at a cabinet, it tells you the width and the height first because that's what you're looking at. Does it fit on my wall? And it tells you the depth last. In this case, since, I don't know how to explain it, but I'm intuitively going with the height being last, but we would get a different answer if we went different ways, okay? So I'm going to go with this fish tank being 10 by 14, not to scale, and then it goes up by 12 inches. Just going to draw this really quick here. All right, so there's our fish tank. Ooh, that was a little off in the back. Okay, so now if this gets dropped by 1/3 of an inch when we take the goldfish out, again, goldfish is all wiggly woggly, right? It's not an easy shape to calculate. If it goes down 1/3 of an inch, then the volume is base times height. The base of this is 10 times 14 times, and what's the volume that got displaced? This time, it's in reverse. It's saying when the fish is in the tank, it's up at the top, and when she's not in the tank, it's 1/3 lower. So we don't care what the original height was. All we care about is the displaced volume when we put the fish back in, is the water level raises 1/3 of an inch. So the volume displaced is 140 thirds of an inch, which, if we divide that, that's what, 40 something, 20 thirds, what's that, 46.6 repeating inches. Now keep in mind though, you would get, if you switch the orientation, a valid answer here could have been 10 times 12 times 1/3. So that would be this and this cancel and you get 4. So you could have gotten 40 cubic inches here and another valid answer. Depending on which of these you chose to be the height, it could have been 14 times 12 and then times the height displaced of 1/3. And so that one, again, the 1/3 and this cancel give you 4. And so in that case, you would have gotten 56 cubic inches. So that was an ambiguously worded question. On a test, I would be much more clear and I would tell you which of these is the base and which is the height. But since it's not clear, any one of these 3 would be a valid answer. I chose to read these first being the base and the other being the height. Okay, good stuff. Let's go to number 4. Oh, so 4 through 9 are saying use this table. This is a real table of densities of different metals. Okay, so what is the mass of a solid block of aluminum if its dimensions are 4 by 8 by 20. Okay, so first let's find the volume. This is a rectangular solid. Okay, so to find the volume of a rectangular solid, we just multiply the 4 by 8 by 20. Whichever two you choose to be the base, it doesn't matter. So we get 4 times 8 times 20. So let's pretend that was the base. So we get 32 times 20. That's 640. So the volume is 640 cubic centimeters. Now we need to somehow convert this volume into density. Now there's formulas, but I like to use units. So 640 cubic centimeters of solid aluminum, we go up here and we go, oh, aluminum tells us that we have this ratio here. So if I want to convert this to mass or weight, I put this over 1 and I want to times by something that's equal to 1. Like this fraction has to be 1, otherwise I'm changing the actual value here. I want to keep the correct value. And what's equal to 1? Well, I want to get rid of centimeters cubed, okay, because that's volume. I want to get rid of that. And I want to turn it into mass. Well, up here we have everything in grams, so let's go to grams. And what number of grams is equivalent to cubic centimeters? Well, we go up here and go, oh, it's 2.81 grams is equivalent to 1 cubic centimeter. So then what we do is in a calculator, I don't have a calculator, pause, unpause, just got that calculator up and going. So we want to do 640 times 2.81. So 640 times 2.81. Boom, we get 1798.4. Whoops. So we get 1798 point. Oh, I'm losing my pen tip. 98.4. Oh, and we crashed. Okay, let's try that again. We get 1798.4. And what are the units? They're in grams. If you wanted to convert that to kilograms, you could really quickly go, well, 1,000 grams is equivalent to 1 kilogram. So I don't know how they want their answer. This is a totally valid answer. But we could cancel that out with grams and get that's equivalent to 1 point. And then we round, and that would be like 80 kilograms or 1.8 kilograms. So either one of those is totally correct. Ooh, let's do another one. That was exciting. So, which has more mass? A solid cylinder of gold, which has a height. So let's draw that cylinder. Okay, has a height of 5 centimeters and a diameter of 6 centimeters. So I'm going to draw a diameter here of 6. This is gold. Or a solid cone of platinum. This is totally a real world problem. I run into this all the time. I'm at the local pawn shop and trying to sell my platinum cone with a height of 21 centimeters and a diameter of 8 centimeters. So first things, let's find the volume. Okay, so the volume of this one is base times height, pi r squared times height. That's pi 3 squared times 5. So that's 9 times 5. So that's 45 pi. All right, then we'll have to, that's in cubic centimeters. We'll have to convert that to mass. And then over here, this one, the volume is 1/3. Oh, and this one, I wrote gold for this one. This one's platinum. Okay, so volume is 1/3 base times height. So in other words, 1/3 pi r squared h, or 1/3 pi 4 squared times the height of 21. 1/3 and 21 cancel, and we get, that's a 7. So that's 16 times 7. Ooh, 70 and 42, so 112 pi cubic centimeters. So it's more volume, but I think platinum weighs less, so we gotta convert this. So the big idea here then is unit conversion. How many cubic centimeters are equivalent to grams? And same thing over here. How many cubic centimeters are equivalent to grams? So I'm going to scroll up. So gold is 19.3 grams per cubic centimeter, and platinum is 21.4. So we don't even need to go any further. 21.4. We have more dense, more volume. So this one does. So we don't even need to calculate it. It's saying height of 21, volume, which has more mass. A solid cylinder, yep. So this one does. I don't even know what the number is, but it's bigger times bigger is going to be bigger than smaller and smaller. So nice. Didn't even need to pull the calculator up for that one. All right. Chemist Dean Dalton is given a clump of metal and is told that it is sodium. He finds that the metal has a mass of 145.5 grams. He places it into a non-reactive, sodium is like one of the most reactive things. So if you drop it in, it could explode. That's cool. Okay. Liquid in a square prism. Okay, so we got a square prism whose base is 10 centimeters by 10 centimeters. Okay, and so here's the prism. It just keeps going up to infinity. All right, and it had some water level, right? Here was the previous water level. And if the metal is indeed sodium, how high should the liquid rise? So what should it go up here if it is sodium? Okay, so what we need to do is take that 145.5 grams and we need to convert it back to volume. Okay, because this is a problem all about volume. So I'll make this over 1. So we need to multiply it by some unit conversion here that gets rid of the grams. And we want to turn it into volume. And our whole table is in cubic centimeters. So how many grams are equal to how many cubic centimeters? So we go up here. And it's sodium. Wait, wasn't it? Sodium, okay. Oh, sodium is down here in the bottom corner. Okay, so 0.97 grams. So in other words, we have 0.97 grams is equivalent to 1 cubic centimeter. So that means the volume is equal to, so 145.5 divided by, so 145.5 divided by 0.97. Oh, 2797. There we go. Oh, exactly 150. That was nice of them. Okay, so the volume is 150 cubic centimeters. Okay. And we know volume is base times height. So we know that this volume displaced here, I'm going to do it in a different color. So the volume here displaced is x height and 10 by 10 base. So let's solve for x then. We get, let's go to green now, that the volume is 10 times 10 for the base times x is the height. So we get that the volume is 100x. And we know the volume should be, if it's sodium, 150 cubic centimeters. So we would expect, unless we were duped, we divide by 100, that the displaced height should be 1.5 centimeters. Oh, and if we did units, this was centimeters, this was cubic or squared centimeters. So when we divide, 2 of the 3 centimeters cancel, and we get this height should be exactly 1.5 centimeters. Now, it's not actually exact because that table is approximate, but we should get 1.5 centimeters going up. If it's different, we were tricked. It's not sodium. Okay, number 7. A square prism containing or container with a base 5 by 5. This time I'm going to do the dashes correct. So dash, 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 dash. Ooh, that was pretty crooked though. 5 by 5. Is partially filled with water, okay? So up here, we got some amount of water. Let's do it's like right here. All right, so it's got a bunch of water in it. Oh, good golly, look at all that water. Okay, dash, 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 dash. Oh, not dash at the top. All right, you drop a clump of metal with mass 525 grams into it. That's the mass. And the water level rises 2 centimeters. And these are both centimeters down here. Okay, what is the density of the metal? And assuming it's a pure metal, so it's not a mixture of 2 or 3 and some alloy. That's what alloys mean. Alloys are really interesting. All the molecules fit together like a jigsaw and do just amazing. I mean, 2 soft metals, alloy, strong super metal. I mean, it's great. How does that work? It's just fit the jigsaw together better. Okay, anyways. If it's pure, what metal is it? All right, well, first of all, the volume displaced here is easy. That's the base of 5 times 5 times the height of 2, so that's 25 times 2. The volume is 50 cubic centimeters. Now, if we want to find the density is how much weight there is per unit of space. So density, again, just use units. All of our densities that are in grams per cubic centimeters is equal to mass, which is in grams, if we're using scientific units, right, with most countries in the world, and then divided by the unit of volume, which there's lots of units of volume, but we're using cubic centimeters right now. So the density is equal to a mass of 525 divided by a volume of 50 centimeters cubed. And so we put that into the calculator and see what we get. I mean, I could tell right now it's going to be around, right, like 1 point. Oh, wow, we don't even need the calculator. What's it going to be? Instead of 1.1, it's going to be 1.05 exactly, maybe? We can double check that really quick. 525 by 50. Oh, 10.5. Got my decimal wrong. Good thing we double checked. Okay, big difference between 10.5 and 1.5. Okay, so 10.5. Let's go up to our table and see what we get. Okay, what metal? Whoops. What metal has a density of 10.5? Oh, exactly, silver. Woo! Winner, winner, chicken dinner. We got a silver nugget here. Okay, so this would be silver. Whoa, that's not a S-L. Yep, there we go. We spelled silver. All right, second to last problem. Lance weighs 174 pounds, and when he completely submerges himself in a 3-foot by 4-foot by 4-foot tank, it rises 3 inches. Again, they do not tell us which is the actual base, which is annoying. So again, I'm going to assume the last one is the height, so the base is 3 times 4. So his volume that is displaced is a 3-foot by 3-foot by, oh, careful of the units, 3 inches. So 3 inches out of 12 inches is 1/4 of a foot. That's the height, right? Because 3 inches, if we convert, right? I like unit conversions. We go times, we cancel out the inches to feet because we know 1 foot is equivalent to 12 inches. So now inches cancel, and we get 3 divided by 12 feet, or 1/4 foot. All right, so that would be the volume is 9/4 cubic feet, or in other words, 2.25 cubic feet. And notice the density of water is given in cubic feet. Whew, that's lucky. If it was cubic inches, we would have to convert. Okay. And now the question is, will Lance sink or not? Okay, well, we got to figure out is his density. Again, density is, we've been using grams per, but it tells us that the density of water is in pounds, which is a different form of mass, or actually it's weight, which is slightly different than mass, per cubic feet. So we're in English units now, not standard or scientific. So over here we get the mass. Again, it's actually weight when it's in pounds. Pounds can be forced too. But anyways, we get mass, which is in pounds, divided by the volume, which is in cubic feet. So we get a weight of 174 pounds divided by a volume of, we got 2.25 cubic feet. So the question is, so this is around what? So 174, 2.25. 77.3. Okay, so we get 77.3 repeating, and that's pounds per cubic feet. Now the question is, will he float or sink? So water's density is this, and this is really on a meta level what's going on with everything in the world around you. I mean, the whole idea of you feeling air pressure here, not up there, what floats, what sinks, air pressure in general. It's gravity is sucking everything down, and it's a constant fight of little balls bouncing around, and the more dense ones can squeeze to the bottom, and they push the less dense ones thing out. And so in a pool, what you have is water, which is fighting to get down, and then some object is also fighting to get down, and whichever one is more dense wins. The less dense thing gets pushed out of the way as the more dense things slide under. Yeah, I'm winning. I'm winning. I'm winning. And this ball just slowly goes up and up because it's not dense enough to win the gravity battle down. This is always what's happening with everything. So the question is, which is more dense? The denser thing will sink. And right here we have Lance's 77 density in the same units as water is 62. So he will sink. Now, when you breathe in air, what that does is it doesn't add a lot of mass or weight, but it expands your chest volume. And that's why when you're like lying on your back, when you breathe in, you expand your volume while not really increasing your mass that much. Air does have a mass. It does have a weight. So you are putting more weight, but it weighs so teeny little, right? We saw it up top. It was like 0.001 grams. And so when you breathe in, it's the same reason a boat floats. The actual individual materials like metals and stuff in a boat are not necessarily going to float. But when you just put that metal container around air, now you have something that will float, right? That's how, I mean, I live in Santa Cruz, and right, the cement ship there, they had a real naval ship. I can't remember if it was like the Santa Clara or something was the name of it, but it was made out of cement. Cement definitely does not sink, or does not float, but when you fill it with air, it does. Okay, let's do a last problem here. Okay, Sherlock Holmes rushes home to his chemistry lab, takes a mysterious medallion from his case and weighs it. It has a mass of 388 grams, okay? Now, let's check its volume. He pours water into a graduated cylinder with a 10 by 10 square base, okay? So let's do it. Let's do it right here. We have a 10 by 10 square base. I'm going to leave out the original volume. And records a water level, which is 53. Oh, no, it does tell us the original. So it starts at 53. Okay. My pen is getting tired. It's so laggy now. He places the medallion in and reads the new level at 54.6. So just subtracting, we get 1.6 is the change in height. 54.6 minus 53. So 1.6 is the new height. All right, so he enjoys a few minutes of mental calculation, turns to Watson. This confirms my theory. Quick, Watson, off to the train station. Holmes, you amaze me. Is it gold? Well, we have enough. Okay, so gold has a density of that, it says. So let's get the volume. The volume equals base times height. So that's 10 times 10 times the height of 1.6, because again, all we're looking for is the displaced water height. We're not looking for that original 53. And so down here, this is 100 times 1.6. So move the decimal twice, and we get 160. Just check the units. The case was 10 centimeters by centimeters. This was in centimeters, so yep, it's cubic centimeters. And then it's saying the density of gold is this, which we had in our chart up above. Whoa, that was a terrible circling job. So let's find the density. Again, density is mass per volume. Again, you could just check the units. It's grams per cubic centimeters is what we were given right up here. Grams per cubic centimeters. So we get 3,088 grams per 160 cubic centimeters. The question is it gold? 3088 and 160. Dun, dun, dun. 19.3. So, crash and reopen. Get down here. So we get that is equal to 19.3 grams per cubic centimeter. And sure enough, is it gold? Yes. And here it says, it's elementary, my dear Watson. Geometry, that is. What is the volume of the medallion? Is it gold? Is it who he says he is? Yada, yada, yada. So, if it is a fake, then so is the kernel. If it is gold, then he is who he says he is. So, kernel, yes. Colonel. What a weird way to spell something. I mean, in English language, that's got to be one of the craziest. Is real. Whoosh. Gold, yes. There's our answer. Woohoo! All right, you guys. I hope you enjoyed the video. Good luck.